Hello everyone and welcome to Lesson 7, the Sine Law and the Ambiguous Case. Part of this lesson will be a review of the sine law, which you learned in grade 10, and the other part will involve something new known as the ambiguous case. Let's get started. Whenever solving problems related to both acute and obtuse triangles, we could use the sine law. You can use the sine law whenever you have a triangle with one of the two following conditions. The first is when you're given the measure of any side and any two angles. We call this side angle angle, or SAA for short. And the second being when you're given the measure of two sides and the angle opposite to one of those sides. This is the side-side angle, or SSA case. When presented with either two, you can use the sine law, which is shown below. We can only use this in triangles that aren't 90 degrees, otherwise we would just use SOHCAHTOA as well as the Pythagorean theorem. If not, you can use the sine law, and we see both versions of the formula shown below. So it takes the ratio of the sine of any angle relative to its side, and these three ratios are all equal to each other. When working with the sine law, however, you'll only use two of the three parts. So for example, maybe you'll just work with angles A and B, or perhaps you'll work with angles B and C. Regardless, we always use two of the three. And you have two versions of the formula. The first one has the sine of the angle divided by the side, whereas the other one has the side divided by the sine of the angle. It doesn't matter which one you use. I would recommend that you use the one with less algebra. Let's try this out in an example. Alright, so we're going to use the sine law to determine the length of side Q. Let me just label that in the picture below. That would be the side opposite angle Q. And side P is the side opposite angle P. And we're given side R, which is 30 centimeters. With that being said, we're going to want to work with angle Q because we have its angle and we want to find its side. And I'd also recommend you work with R because we have both the side and the angle for R. So let's do that. I'll start off by writing out the sine law. Q over sine Q equals R divided by sine R. And the reason I chose this form of the equation is because we're looking for side Q, and it's much easier to isolate for it like this. I'll show you what I mean. Since we want to isolate for side Q, let's just multiply both sides of the equation by sine Q, like this. Okay, and now that we've done that, we've isolated for Q, we just substitute and we're done. So side R is 30 centimeters, multiplied by sine angle Q, and divided by the sine of angle R. Okay, so working this out on your calculator, and please make sure that you're in degree mode, you should get a side of approximately 31.6. Alright, and we'll wrap this up with a therefore statement. I'll always write the units in the final therefore statement just to avoid cluttering the equation. Alright, we'll do another one. In this one, we're asked to use the sine law to find angle E right here. And there's a small typo here. Please change the 9 millimeters to 9 meters. The units should be the same. Okay, so with that being said, we want angle E, so I better work with E. And notice that we're conveniently given angle D as well as its side. So let's work with D and E in this example. I'm going to use the version of the sine law that has the angle in the numerator. So sine of angle E divided by side E is equal to sine of angle D divided by side D. Solving for angle E, we can multiply both sides of the equation by side E, like this. I'll isolate for angle E by taking the inverse sine of both sides, like so. Okay, so we've isolated for angle E. Now we substitute all of the values and solve. Once again, I'll write the units. Once again, I won't write the units while I'm doing the algebra. All right, and working this out on your calculator, you should get approximately 34 degrees. Once again, please make sure that you're in degree mode. All right, and we'll do one more. This one asks us to use both the sine and cosine law to find the length of side CD. I'll just label that in the picture. I'll call it X. And that's going to be the side that we're looking for. So this question said that we need to use both the sine and cosine law, and I'll show you why. If you look at triangle CDE, we only have two angles. With just two angles, you don't have enough information to find any of the sides. You would need at least one other side. So what we're going to have to do first is work with triangle DEF. And whenever you're given a problem like this where two triangles share something in common, for example, in this case it would be side DE, we'll work with triangle DEF to find the thing that they have in common. I'm going to label that lowercase f just because it's opposite side f, and we'll use the cosine law in this triangle. Recall, you can use the cosine law whenever you have side, angle, side. That's an angle sandwiched between two sides. In this case, angle F, which is 97.4 degrees, is wedged or sandwiched between sides D and E. So the cosine law is as follows. F squared equals D squared plus E squared. Take away 2 times D times E multiplied by the cosine of angle F. Now we solve for F, so I'm going to do this in one shot. We take the square root of both sides. And now I'm just going to substitute for DE and angle F. Okay, so side D is 2.5. Side E is 3.9. And we multiply by the cosine of angle F, which would be the cosine of 97.4. Okay, everyone, so you have to use BEDMAS when you're solving something like this. What I mean is the following. Notice that we have 2.5 squared plus 3.9 squared, and we're subtracting this big product, which I'll highlight. That thing I've highlighted becomes one number. So you'd have to work out 2.5 squared, that gives you a number, then add that to 3.9 squared, which is another number, and then subtract that big product I've highlighted. After you've done all that, take the square root. So I'll give you a moment to do that on your calculator. I recommend doing it in one shot just to avoid rounding errors, but after doing so, you should get a value of approximately 4.9. If your answer is close to 4.9 but a little bit off, maybe it's because you did this in steps rather than one shot, which introduces a bit of round off error. That's more of a big deal in the sciences, and math not as much, but it's just something I'll mention. Alright, so now that I have side F, let's go to triangle CDE. And in that triangle, we have to find side X. So right now we only have two angles, which isn't enough information. We have one of the sides, but in order to use the sine law, we should find the angle opposite that side. So in this case, let's find angle C, which is the angle opposite the shared side. Recall, three angles in a triangle have to add up to 180 degrees. So thus, angle C is equivalent to 180 minus 56.7 minus 48.2. You should get 75.1 degrees. And we're pretty much all set now. We have an angle side pair for C, we have angle E, and we're looking for X, which would be equivalent to side E. That's the side opposite angle E. So I guess I'll still use X just to be consistent, but if you use another variable or E, it's fine. Okay, so X over sine E equals side C over sine of angle C. Please don't be confused with my labeling here. Side C now would refer to the shared side. I called it F before, but in the green highlighted triangle it would be C. Solving for X, we have the following. C multiplied by the sine of angle E, all divided by sine C. Plug in the values that we have, so side C, which is the shared side, would be 4.9, multiplied by the sine of angle E, that would be the sine of 56.7 degrees, and all of that is divided by sine of angle C, which we just found, so that's the sine of 75.1 degrees. Alrighty, so working this on your calculator, you should get approximately 4.2. Alright, so therefore, the length of side CD is 4.2. In this case, it would be meters, just keeping with the same units from before. Alright everyone, so that was a quick review of the sine law from grade 10. And now we're going to move on to the ambiguous case, which is something new. But first, in order to motivate what the ambiguous case is, I have a little surprise for you. So take a look at the picture below, and I want you to write down or say to yourself the first thing that you see. Please pause the video and do so. When you're ready, click play to resume. Alright, so believe it or not, there's actually two answers to this question. Depending on how you look at the picture, you either saw an old woman or a young woman. So where's the old woman? Let me just highlight. This would be the nose of the old woman. Do you see it? So that's her nose. This would be her mouth. And that's her chin below. And it looks like she's wearing some sort of a fur coat. And it appears like she's wearing some sort of a hat. This would be her eye. And this looks like a bump or maybe a wart on her nose. And that's the old woman in the picture. But there's also a young woman. Let me show you what I mean. If you saw the young woman, you're looking at a side profile of her face. So this would be the side profile of her face. That's her chin. This is her neck. It looks like she's wearing a necklace. We're looking at her ear over here. And that's the side profile of her nose. and this would be an eyelash. Okay, and this young woman is also wearing some sort of a hat, it looks like, and she's wearing the same fur coat. So I guess I can't ask you in person what you saw, but it would be interesting if in the comments below you posted what you first saw, either the old woman or the young woman. And the reason why I'm showing you this picture is because it's ambiguous. There's no right or wrong answer. You either saw a young woman or an old woman, and hopefully now you see both. But I want you to keep this in mind because it's what we're talking about in math. So you may be wondering, what does ambiguity have to do with math? Well, let's find out. So to get started with the ambiguous case, please complete the following warm-up. You can work these out on your calculator. Please pause the video and click play when you're ready to resume. Okay, so here we go. I asked you to determine each of the following to the nearest tenth. That would be 1 decimal place. So sine of 45 and sine of 135 should both give you approximately 0.7. Sine of 5 degrees and sine of 175 should give you both approximately 0.1. And sine of 140 and sine of 40 degrees should give you both approximately 0.6. We actually looked at this when we learned about the cast rule, and please also notice that in all three examples, the two angles are supplementary. In other words, they add up to 180 degrees. So what we're seeing here is that the sine of any two supplementary angles will always produce the same value. Now, as another point to make, let's say I asked you to do the sine inverse of 0.5. Please do so on your calculator, and your calculator will definitely give you 30 degrees. And if you take the sine of 30 degrees, you'll get 0.5. But take the sine of 150 degrees and see what you get. Sure enough, it's also 0.5. So when you do the sine inverse of 0.5, you could get either 30 degrees or possibly 150 degrees. And you may remember we saw this with the cast rule as well. So for example, in this case, the angle could lie in quadrant 1 or quadrant 2. But this is what I mean by ambiguous case. Notice now when you take the inverse sine of 0.5, you're getting two possible answers, 30 degrees or 150, an acute angle or an obtuse angle. This is what we mean by an ambiguous case. It's like the picture on the previous slide when you saw that there could have been an old woman or a young woman. And that's exactly what we're going to do today. Let me show you what I mean in a more practical example. In example 4, we're going to look at a triangle where angle A is 29 degrees, side B is 21 centimeters, and side A is 13 centimeters. We're going to draw two possible triangles for angle B and then solve both of them. But I'm going to have to show you what I mean over here. So let's get started with the first one, case 1. Let's say angle B is acute. It'll help if we label what we have. So angle A is 29 degrees, side A is 13 centimeters, and side B is 21 centimeters. I told you in case 1 that angle B is acute, that is less than 90, and you can see this in the picture below. So we were asked to solve both triangles. Let's get started and do that. In this triangle, we're given an angle and two sides. So that's side-side angle. We'll use the sine law. I guess the first thing we can do is solve for angle B. So sine of angle B over side B equals sine of angle A over side A. Solving for angle B, I'll do this in one step. It's going to be the inverse sine of side B multiplied by sine of angle A divided by side A. All right, plug in your values and we'll work this out on the calculator. So angle B is the inverse side of 21 multiplied by the sine of 29 degrees. All of that is divided by 13. Okay, and working this out on the calculator, you should get about 52 degrees. Let's just round it to the nearest whole number, and you'll see why shortly. It makes it much easier. Remember, we have to solve this triangle, so we have two sides and two angles. I guess the next thing that we can do is solve for angle C, because all three angles have to add up to 180. So angle C would be 180, take away 29, take away 52, and that's going to equal 99 degrees. All right, we're pretty much there. We have all three angles and two sides. The only thing left to do is to find side C. And to do that, I'll use the sine law once again. So side C over sine C equals, and you could use either A or B in this case, it doesn't matter. I'd actually recommend you use A though, just because that was provided to us in the original question. So in case if you made a mistake finding angle B, it won't carry through. All right, so that's going to be side A divided by sine of angle A. And now we plug in our numbers and solve for C. So just to save a bit of room, I'll do this in one shot. C is going to be side A, which is 13, multiplied by the sine of angle C, which would be sine of 99, divided by the sine of angle A, which is 29. And working this out on your calculator, you should get about 26. Now, where is the ambiguity here? Case 1 was when B was an acute angle, but in case 2, I'm asking you to look at it for B being an obtuse angle. What do I mean by that? Well, on your calculator, when you did the sine inverse of 21 times sine 29 all over 13, we got an angle of 52 degrees. But remember the picture with the old woman versus young woman? How am I guaranteed that it's really 52 degrees? What if it's the obtuse angle? And what would the obtuse angle be? It would just be 180 minus 52. So let's work that out. For the obtuse case, angle B would be 180 minus 52, which gives us an obtuse angle of 128 degrees. Right here. Angle A is still 29 degrees, that hasn't changed, and side A is still 13. So that hasn't changed. The only thing that changed right now was angle B. And this is probably the most confusing part of this, but just to show you what I'm talking about, take a moment please, work out the sine of 128 degrees, also work out the sine of 52 degrees, and just verify that they're the same. They should be, and that's because they're supplementary angles. They add up to 180. So once again, this is the ambiguity. Angle B could either be 52 or it could be 128 degrees. Which one is it? We honestly don't know. This is why we have to do the two cases. Once again, one of the angles is like the old woman in the picture, the other angle is like the young woman in the picture. This is what I mean, everyone, by the ambiguous case. We don't know. And what makes this so hard is this is probably the first time in math where something could be either or. Up until now, math was very objective. It was right or wrong. But this is what makes this lesson so interesting. There's two possibilities and we have to consider both. All right, so let's carry on then. We're going to solve the obtuse triangle. So if angle A is 29 degrees, and if angle B is 128 degrees, then we can find angle C. it would just be 180 minus 29 minus 128 degrees, and that's going to work out to give you 23 degrees. So now we have all three angles, and we have one side. Actually, we have two sides, sorry. I forgot to label side B. Remember, that's still 21. So I just want to remind you for one moment of the three things given in the question. We were given angle A, side B, and side A. Because those were given in the question, they're not ambiguous. And we work with those. So we're actually almost pretty much done. We just have to find side C, and to do that, I'll use the sine law. So C over sine C equals, and again, you can work with A or B. I'm going to stick with A over sine A. All right, solving for C, it's A, and I'll just substitute to save a bit of room. So it would be side A, which is 13, multiplied by the sine of angle C, which is the sine of 23 degrees, all divided by the sine of angle A, which is the sine of 29 degrees. And working this out on your calculator, you should get approximately 10. All right, so let's just summarize. And I guess I'll fully label the triangle with everything we found, so just give me a moment to do that. And even for the acute triangle, let me just take a moment to label everything. All right, so this is the thing to take away from this lesson. When you take the inverse sine of a number, your calculator will always give you the acute angle. However, it could also be an obtuse angle. So that means whatever angle you first take the inverse sine of, in our case it was angle B, which I'll highlight here, your calculator gave you 52, but what we're learning today is that it could also be 128 degrees. So we have to set up a second triangle with the possible obtuse angle and solve them both to look at all possibilities. That is the ambiguous case. So we have a way actually of checking whether or not the ambiguous case will produce one or two triangles, and we're going to go through all the cases. So to generalize everyone, the ambiguous case is actually more broadly a situation involving the sine law where we could produce either 0, 1, or 2 triangles. I'd really like you to highlight this. It only occurs whenever you're given two sides and an angle opposite one of those sides. So it's only going to occur for the SSA side-side angle case. Here are the conditions to determining the number of possible triangles. And to do that, we're going to look at the picture below to help us. So we have triangle ABC. Notice that side A is opposite angle A, and side B is opposite angle B. Also notice I drew the height of this triangle, which would be from the base to the top. What I'm going to do now, and this will help us out later, we're actually going to use the height to help us determine which case it is. But to do that, we need to get an expression for the height. So please take a look at this triangle that I'm highlighting below. So please look at the triangle that I'm highlighting below. And for that triangle, we're going to come up with an expression for the height. So in the triangle that I've highlighted, if you come up with an expression for the sine of angle A, that's just opposite over hypotenuse, which is equivalent to h over b. Solving for h, we get that the height of the triangle is equivalent to side B multiplied by the sine of angle A. This is going to be our condition that we use to help us determine whether we have 0, 1, or 2 triangles. Let's go through the different conditions now. Our first condition is what happens when side A is less than the height of the triangle? Well, look at the picture below. If side A is less than the height of the triangle, then side A isn't actually big enough in order to complete the triangle. So when this occurs, there are actually no possible triangles. Okay, the next condition is what happens when side A equals the height of the triangle? Well, in that case, everyone, side A fits in perfectly right here, and therefore the only triangle that we form is the 90-degree triangle shown. So in this case, we only form one possible triangle. It's kind of like a Lego piece, if you will. That side fits in perfectly over here, allowing us just to form the right angle triangle. For the next case, what happens when side A is larger than the height and side A is larger than side B? When that occurs, side A is too big to fit over here. It's longer than the height. So therefore, the only possible triangle would be this acute triangle that I'm highlighting in red. Okay, in that case, we just produce the 1. And the last case is perhaps the most interesting. What happens when side A is larger than the height and side A is smaller than side B? Well, in this case, we have two possibilities. Looking at the picture below, I want you to focus on these two sides that I'm highlighting. Those both represent side A. And this point up here, I want you to picture that's like a pivot point, and side A can swing back and forth. In other words, it can oscillate in this direction, okay? Because side A is bigger than the height, it's able to form two triangles. Let me just highlight them. So you have to give me a moment here to clean up the diagram. One of the triangles that we can form is this obtuse triangle that I'm going to highlight. But another possible triangle is this acute one that I'll highlight in yellow. Like that. All right, so when side A is bigger than the height, but also smaller than side B, this is the only time where you form two possible triangles. Okay, everyone, so those are the different conditions for the sign law and the ambiguous case. I know that was a bit confusing. If you need to rewatch that part of the video, please do so, but I'm going to show you next how we actually apply this. So here's our procedure for solving ambiguous case related problems. First of all, you only ever have to worry about this when you're dealing with the sign law. If you're just using the cosine law or the Pythagorean theorem or SOHCAHTOA, you don't have to worry. It's just for the sign law. Next, you have to make sure that you're given two sides and an angle opposite one of those sides. In other words, the side-side angle scenario. If you're not given two sides and an angle, just use the sine law like you normally do. You don't even have to worry. It's just when there's a side-side angle that you have to worry a little bit. In step 2, sketch a diagram, and then using the table on the previous page, determine which condition it is. If two triangles are possible, use the sine law to find the missing angle, and that would be opposite to the attached side, and that angle would be one possible triangle with an acute triangle. In the other case, the same angle could be obtuse, so you would have to find that by doing 180 minus the angle, and then just like we did in the first example for the ambiguous case, you would solve them both separately. Okay, so I'm hoping this will make a little more sense in an example. Let me demonstrate. In example 5, we're asked to determine the number of possible triangles, so not solve them, just determine how many possible triangles there are in triangle ABC, where we're given angle A, which is 40 degrees, side A, which is 10, and side B, which is 15. So first of all, notice that we're given two sides and an angle. So this would be the SSA condition, which is what you have to worry about when it comes to the ambiguous case. Let's sketch a picture. And I'm going to stick with the same way that we were drawing the triangle before, meaning I'll put the angle that we were given in the bottom left. That's our 40 degrees. The side opposite angle A is 10. And just to be consistent, I'll put B in the bottom right and C at the top, and then side B is 15. So notice we were given one angle and two sides, and one of the sides that were given is opposite the angle that was provided. Well, is this an ambiguous case or not? We're not sure yet. We have to determine the height because the height will allow us to check the conditions. So I wrote this for you on the previous page, but remember the height is equal to side B multiplied by the sine of angle A. Let's work that out. So that would be 15 multiplied by the sine of 40 degrees. And working this out on your calculator, you should get about 9.64. Now, I'm going to keep two decimal places here, and the reason being, when you're rounding, that can actually give you an incorrect result. So just to be safe here, I'm going to keep a few more decimal places to make sure I'm aware which of the four cases from the previous page we're dealing with. So let's compare the height to side A. Notice that side A is larger than the height, but how does side A compare to side B? Well, side B, which is 15, is larger than side A. So A is greater than H, and at the same time, A is less than B. Which of the four cases are we dealing with here? It's the last case, where A is larger than the height, and at the same time, it's less than side B. So all we know is that there's two possible triangles, and we're done. In this question, we were just asked to determine the number of possible triangles. Let's say the question asked you to solve them. Now that you know there are two possibilities, what you would do is the following. You would set up two cases, just like we did in example 4. Do you remember this one? You would draw the two possible triangles, one where angle B is acute, the other where it's obtuse, and you would solve them separately. All right, let's do one more example. Determine the number of possible triangles for triangle XYZ, where we're given angle X, side X, and angle Y. So I purposely chose different letters over here, but you can set it up the exact same way like before. So first of all, it doesn't matter how you label this, it really doesn't. But what I prefer is to put the given angle in the bottom left corner. That was angle X, which was given as 20 degrees. The side opposite this is X, which is 3. We were given side Y, The other angle that could be ambiguous, I'm going to put that in the bottom right corner. That would be angle Y. That's like the B in the previous question. And then side Y is 10. That would be opposite angle Y. And lastly, we'll put angle Z at the top. So that's how I like to label these pictures. For the angle and side pair that I know, I'll place that angle in the bottom left. For the angle side pair I don't know anything about, in this case Z, I'll put it at the top. And for the angle side pair where I know just the side and not the angle, I'll put that angle in the bottom right. And how do I know this is an ambiguous case question? I know it is because I'm given two sides and an angle. So this is the side-side angle condition. That's the only time you have to worry about the ambiguous case. So remember, we need the height because the height is what's going to allow us to determine how many triangles we're dealing with. Now, before, we just used the formula b multiplied by sine A, but look at this picture and think about it. You're going to look at this triangle that I'm highlighting. In that triangle, we have angle x, side y, and the height. So sine of angle x is opposite over hypotenuse. Solving for h, we get 10 multiplied by sine x, or 10 multiplied by sine 20. And that's going to work out to give you about 3.42. Remember, I'm keeping some extra decimal places here just to avoid any possible round-off error. And now we compare. So compare h to side x. Well, notice that side x is less than the height. Now we're dealing with side x, but this was analogous to side A. So which condition is that? That would be the very first one. Now in my picture it looks like I can form a triangle, but let me just explain this a little further. I guess what we're saying is we didn't know how big that side was, but apparently since that side is smaller than the height, it's not going to be long enough to make a triangle. It's going to sort of fall short. Now you may be wondering, how do I know that? Well, aside from it just being one of the conditions, let me make this a little more clear. Well, aside from that just being one of the conditions, let's make it a little more clear. I'm going to highlight this part of the triangle in red. What's the longest side in any triangle? It's the hypotenuse. In this case, it would be the side with a length of 3. But I just showed you that that side of length 3 is smaller than the height, which is one of the other two sides. Because the hypotenuse of this triangle in red is less than one of the other two sides, we can't actually form a triangle here. This is why there are no possible triangles. All right, and that's going to wrap up this lesson on the sign law and the ambiguous case. Like I said, it's definitely a challenging lesson, so if you have any questions, please let me know. And there's some recommended homework for you to practice here. So, thanks for watching everyone. I'll see you in the next video.